Okay. Yeah. Good afternoon, everyone. So my name is Abhishek Dhar. So I'm a theoretical physicist working here in ICTS, and I work in the area of statistical physics. And basically, I'll try to give you some idea about the kind of work I do through some sort of simple example. So statistical physics is about randomness, and so that's how randomness comes. And when you work in statistical physics, the idea is to, in spite of all the randomness, you can still make sense out of and get things which you can predict and so on, right? That's the idea of statistical physics. So we look at random systems, but can still make useful predictions. So this is what I'll try to explain. So please feel free to ask questions at any point. And later, like I'm at ICTS, so anytime you can come and ask me. Okay, so, right, yeah. So I'll start by talking about this, some experiment. So by the way, how many of you have done one course in statistical physics? Okay, so maybe around 30% or something. Okay. So let me talk about this machine called the Galton probability machine. Uh, so, okay, so what you see here, and I'll show you actually a demo. We made this machine at ICTS, and I'll show you how it works. So let me first just show the experiment. Okay, so what you see here is basically there is okay, so there's a funnel here, and we will drop marbles or grains from here, and they will flow down this channel. And in this area, there are a lot of pins, okay, which scatter the marbles that are falling from the through the funnel. Okay, so there are a lot of pins which are placed on a triangular lattice, and then as they fall, they get kind of scattered, and then they collect in these bins. Okay, so here there are a lot of bins. Okay, so let's look at the experiment. Okay, so here I'm just collecting stuff in the funnel, and then we tilt it back, and then, okay, so you can see something happened. Okay, so this is just a repeat of the experiment. Okay, and then we'll see it in kind of slow motion. So these are steel balls that are being dropped from this funnel, and then they're getting scattered by these pins out here, and they get collected in various bins. So there are a lot of bins out here. Okay, so they're getting collected. What you see is eventually there is a large number of bins get collected at the center. At the edges, it's much less, and so on, right? So there's a distribution of like number of bins collected in each of these number of balls collected in each of these bins. And okay, so now, okay, and you see there's a curve here, okay. So this curve is actually some curve which you all know, it's a Gaussian distribution. And you can see that, I mean, this somehow the distribution of balls, it fits nicely to this Gaussian curve, right? Okay, so this is what you observe. The chaotic motion of many, many balls leads to some order in the distribution of the number of balls in the boxes at the bottom. Okay, so even though the balls are doing something completely random and so on, each ball is doing moving randomly. At the end, when we collect a lot of balls, we see that there's a nice pattern that is formed, right? So this is one of the ideas that I want to talk about. So what you see is more balls at the center, less at the sides, and a nice bell-shaped curve, which is a normal or Gaussian distribution, a very popular function in physics. Okay, so I think, what do I have? Okay, so I'll just tell you a little bit about how this Galton board was discovered. So it was discovered by this person called Sir Francis Galton about more than 100 years back. And he actually, basically he wanted to demonstrate exactly this, that random events can lead to patterns, okay. So he was someone who was interested in various things like weather and, I mean, there are lots of things, okay. It's an amazing person. But he made this simple device that we are now trying to replicate here. And this was just to use as a popular demonstration of how random things can still lead to order. Okay, so you can buy it on Amazon, but it's better if you try to make it on your own. It's much more work, but I think it's a good exercise. Okay, so I later will demonstrate what we have managed to get out here. Okay, so first let's just try to understand a bit like how does this pattern emerge? Okay, what can we say precisely about this pattern? Okay, so if you, so basically the idea is that if you look at, so what is the system, right? Okay, so basically we have a set of pins placed on a triangular lattice. So I'm just marking them in some way. So I place these scatterers or pins on a triangular lattice. Okay, so it's a nice triangular lattice. And then, okay, so this is the 0th step, and this is 1, this is 2, this is 3, this is 4. And then at the end, I collect them. Okay, so I collect them in boxes. So I put boxes like this. Okay, so now when I drop a ball, let's say I drop a ball here, I mean, what does it do, right? So it does a random walk. So, I mean, it hits, so there's it's kind of a pin here. And when it hits, it depends on where it strikes the pin. If it strikes slightly here, it will move this side. If it strikes slightly here, it will move this side, right? So on an average, whenever it goes down, it does a random walk, okay? So one possibility is that the pin goes like this, then it goes like that, like that, like that. This is a possibility, right? And then it goes like that, and it ends up in this box, right? After 1, 2, 3, 4, 5 steps, right? So at the end of 5 steps, there's a possibility that it ends up in this position. Now, there's also a path, like it can go here, it can come here, it can go like this, and it can end here, right? So there's one more path which goes like that. Okay. So, okay. So now there's some big difference between this path and this path. What is the difference? Second one is it? I mean, okay. See, they're both equally likely. You can't say because at each time step, I can go this way and this way with equal probability, right? So if I ask what is the probability of going from here to here, it's 1/4. This is 1/8. This is 1/16, and then here 132, right? But if I ask what is the probability of this path, that's also 132 because at each step it's half, 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 right? So they are both equally probable. Okay, but how come I got more balls here? Sorry? Yeah, right, exactly. So here there's only one path, right, which can go here. But here I easily construct one more path, which is, let's say, and that, right? So there are a number of paths which, I mean, you can see there are lots of paths which will go here, but there's just one path here. And we can compute the number of paths that land up at various places. So, and from that, we can figure out what is the number. Okay, so let's just do that. So I have some, so this is, I have some slides which explain this idea. Okay, so each ball performs a random walk. So this way you can kind of think of like this way is time and this way is space. At the end, I can land up at various places, and this is like each step is like a time. Okay. So at each step, it can go to the left and right. So in this case, after 1, 2, 3, 4, 11 steps, it lands up at position 5, right? So I mean, if you think of like one step walks, then there are two possible walks, and both they land here and here. For step two step walks, they can go to 3 possible places, and there are 2 paths like this, one path, right? Then 3 step walks. If you each step 2 possibilities, 3 steps 8 possibilities, right? So there are 8 possible paths. And if you just see how many paths go here, there's one path. Out here, you can count there are 3 paths which land up here and so on, right? So you can count how many paths. And if you do it for more number of things, you'll get some pattern like this. And yeah, this you all have seen, it's called a Pascal's triangle, right? So there are some numbers here. Okay, so okay, and from these numbers, we can, this number should reproduce that curve we saw, right? Because everything is happening with equal probability. So the number of balls that reach here will be proportional to this number and so on. Okay, so so if we plot the number of numbers at the bottom of the Pascal triangle, we basically get this bell-shaped function. And this function, okay, so we'll just work this out quickly. If you ask like how many paths are there at which reach every point, then you can count it and it gives you this. And in some limit, it gives you a Gaussian distribution. Okay. So let's quickly try to, so this function is the normal distribution. And this is exactly what we saw in the Galton board. Okay, so it's a very simple way we can understand this thing. So let's quickly try to calculate this number that we have here, because it's, I think many of you would have already done it. So basically we ask, let's say if you take n steps, right? Then we want to, so then the number of paths is how many? If I go n steps, what is the total number of? 2 to the power n, right? 2 to the, so let's say number of steps, that is the number, this is 1 step, 2 step and so on. Number of steps equal to n, number of paths equal to 2 to the power n, okay. So now we want to see how many paths land up at some point x, okay. So here x goes from, let's say, this is 0, this is -1, -2, -3, -4, this is -5. Okay, so -5, -4, -1, 1. No, sorry. This is -1, -2, -3. -5. Okay, this one is -4. This is -3. This is -2. Okay, so this is the ball center is at 5. This wall is at 4. Okay, so if you take an odd number of steps, you can only land up at odd places, right? Or odd number boxes. So at 4, there can't be anything because you can go either here or here. So you can be at -5, -3, -1, 1, 3, and 5. Okay, so now the question is how many paths are there which lead up to, let's say, some point x. Okay, so to reach some point x, what we see here is that you have some number of steps which go to the right and some number of steps to go to the left, right? So and so one possible is like it goes left, right, right, left, right, right. So this is 1, 2, 3, 4, 5, 6. 6 steps, right? So this is n equal to 6. Okay, so so this is left, right, right, left, right, right. Okay, so we see that number of left steps is number of left steps is how many? 1, 2, 2, right? And number of right steps is 1, 2, 3, 4. Okay, so if you take so many left steps and so many right steps, then finally the final position will be what? Right steps minus left steps, right? So that is x. So x is just n right minus n left. And we know that the total number of steps is nr plus nl, right? So, so our final goal is that after n number of steps, how many paths lead to x, okay? So now I can, for the same point x, I can do lots of left and right combinations, but as long as the total number of nl and nr are fixed, it's guaranteed that I'll reach x, right? So basically, I have a sequence of, let's say here, 2 L's and some rights. So this one is a sequence L, R, R, L, R, R, right? So this sequence of left rights take me to x equal to what? X equal to 2, right? Now I can interchange any of them, right? Keeping number of L's and R's fixed, I'll always get 2, right? So if I ask how many paths are there which lead me to x equal to 2, how many is it? It is, so there are 6 things and I have to choose 2. It is 6 choose 2 or 6 choose 4, right? It's the same thing. So these are the ways I can arrange 2 L's and 4 R's in all possible ways, right? That will give me how many paths. So all these are distinct paths, obviously, because every time I change them, it's a distinct path, and all of them will take me to x equal to 2. Okay. So therefore, you can see that in general, if I have a total number of steps n and I want to reach x, then I have to take so many nl steps and nr steps which satisfy this. So then, what is the number of paths? N factorial divided by, yeah, NL factorial and NR factorial. And this NL and NR we know in terms of, we can solve this equation and find NL and NR in terms of N and X, right? So the final number of paths, let me just use the other side. Okay, right. If you solve for NL and NR with those two equations, then we just get this. Okay, so this is the this is exactly what I have. And what is this 1 by t to the 2? So this is the total number of paths, and each of the paths. Okay, so t and n are the same. Okay, so what I called n and t are the same, and factor 1 by t to the 2 is just the total number of possible paths, right? So that therefore this gives me the probability distribution, for each path. Okay, so this is what we get, and then how do we get the Gaussian from here? Why is this the same as the Gaussian? Okay, so this is some basically some approximations that you have to make, and it's a very nice approximation. Okay, so this is the number of steps, and then like I said, probability. If it's a random walk, you can say probability of reaching x is equal to, because this is the total number of possibilities and each possibility has probability 1 by 2 to the power n, right? So just this divided by n minus x by 2 factorial. Okay, so this is what we have here. Okay, now how do we get the Gaussian from here? So there's something called Stirling's approximation. So in physics, it's always like factorials and all are very complicated objects. So you always good to make some approximations which are valid when numbers are very large. Okay, so this is called Stirling's approximation, which is basically saying that if you take n factorial, then it's almost approximately equal to n to the power n to the power minus n square root of. Okay, so this is it's a famous approximation, but it's even though it's an approximation, it's actually extremely good. Okay, so I encourage you to just put values for like n, let's say n equal to 5 here, and then do the exact value which is 120, and do this approximate value. You'll find that they're extremely close. Okay, and as n becomes larger, this gets better and better. Okay, so now if you use this approximation in this formula, then after doing some simplification, you'll immediately get this Gaussian distribution. Okay, so that's the idea. Okay, so this I just changed the notation bit here. T, n is t, and x is n. Okay, so I mean, just as homework, I like what you should all try is, in case you have not done this before, just take two-step random walks and verify that this formula is correct, and just draw all possible paths and check that this makes sense. Okay, so then you'll really remember this formula. It's a nice, simple formula. Okay, so. Okay, so this is our first example of how you get a pattern out of completely random events, and we got introduced to what is the random walk. So now I'll tell you a bit about the history of the random walk, which is also very interesting. Okay, so it was first yeah. I think probably one of the first times it was discussed is this example. So you have heard of Ronald Ross, who discovered that I mean how malaria is transmitted and so on. I think he did it in Calcutta, yeah, in some hospital in Calcutta. Okay, so he was interested in mosquitoes. So one of the things he was interested in is, like, if you have a swarm, like a huge population of mosquitoes, how do they spread? Okay, so this is a practical problem. Okay, so he wrote to some a scientist called Carl Pearson in 1904 asking for help. And his question was basically this. So there's this journal called Nature where he wrote this, he posed this problem. Okay, so can any of the readers refer to me a work wherein I should find a solution of the following problem? Okay, so this is the problem. So the problem is basically he's asking, so this is a problem basically about a random walk. A man starts from some origin, let's say O, and he walks 1 yard in a straight line, and then he takes turns through some angle, some random angle, right? So he turns and then takes again 1 yard, and then again takes a random angle, moves 1 yard, and then does so on, right? So he keeps doing this, and let's say after n steps, then the question is, it's a random process, right? So if you do it once, if I do a random walk, I might, after 5 steps, I might be here, but there's a possibility I could do after 5 steps, I might be somewhere here, right? So there's all possible places I can be with some probability. Okay, so then you want what he wants to know, what is the probability that if I start from here, after some distance, after some n number of steps, what is the probability that I am in some region between R and R plus dr? Okay, so this is the question. Okay, so I mean, since you are moving in all possible directions, it's clear that it has to be after some time. I'll be on there's some spherical symmetry, right? So I should be on some radius of roughly localized on some radius r, and the question is, what is the probability of being in this region? Okay, so at that time, no one knew how to answer this question, and this question was seen uh, by Rayleigh, who actually solved this problem. Okay, so he was actually thinking of some other problems. He was thinking of waves coming and randomly and interfering, and that he realized that these two questions are basically the same, and he was able to solve this problem. So see here, basically, it's a simulation of this process. Okay, so here what I show is like after n steps, I just plotted the position of the walker. Okay, and for different realizations, it can be in different places. And then you ask what is the probability? It's between these two circles. Okay, so you can count how many processes ended between these two circles, and you get a distribution like this. Okay, so this curve that you see here is exactly this function. So it's a Gaussian, but then there's a 2 pi r factor coming from the fact that it can be anywhere on the radius. Right? So that's why it's r times this. Okay, so here also you eventually finally it's a Gaussian process. It's a Gaussian distribution in 2 dimensions. But if you ask between r and r dr, you have to multiply by 2 pi r, so you get this extra factor, and then this is the distribution. Okay, so this was proved by Rayleigh, and he wrote to Pearson, who wrote to uh, Ronald Ross. So Yeah, so in some sense, just trying to understand how mosquitoes move and see mosquitoes basically. So, I mean, what do you learn about mosquitoes from here? So you learn that it doesn't spread too fast. Okay, so it spreads if you look at how much in time t, how much distance they have traveled, it grows as square root of t. Okay, so this is one of the important things about diffuse. This is like a diffusive process. And okay, so again, this is an example of like completely random events, but you can make definite predictions of how they of some properties. Okay, so random walks are everywhere. Uh, so what the example I give you is an example from ecology, but they were around the same time. Actually, people were also looking at things like just prices of stocks in markets. Okay, so they are randomly fluctuating, and you can understand a lot of things by modeling them by random walks. Okay, so they were used in finance quite early on, and then they have, of course, used in mathematics, statistics, and computer science. There are all sorts of interesting problems, just as a maths problem. And in astrophysics, so there's a very famous article by Chandrasekhar in 1943 on the random walk. And in statistical physics, I'll talk a bit about one of the most famous random walks, which is Brownian motion. Okay, any questions? Yeah. What was the? Yeah, they can't. Yeah, I mean, typically you see mosquitoes. Okay, they move like that, but this distance is much more, right? So it's quasi 1D maybe, quasi 2D. Sorry. Yeah, there was another question.
Uh, yeah, sir. In the random walk which you just described,
Yeah.
after every turn, is the angle same or at different angle?
Oh, good question. Okay, so after it doesn't matter. Okay, so if it's of course the same angle means if it does like let's say if it does 30° every time. Okay, then of course it does. It moves like that, makes 30 degrees again, makes 30° again. Then it's not going to do much, right? So in this case, what I said is that the angle is random, also chosen randomly. So at every time step, you choose the angle randomly. Yeah. Okay. The solution. Uh, okay, maybe I'll do it at slightly later point where I. Yeah.
That the mosquito will not may go forward and can come back like backwards. It can move in backwards.
Yeah. So you see, if you look at each mosquito, it's going. I mean. See, I mean, if you look at, I mean, this is what a mosquito does, right? It's, of course, it's going backwards sometimes. Okay, that's what it's doing, right? So of course, it's allowed to go sometimes backwards. Okay, so each mosquito is doing something, but you take another mosquito, which I mean, which might do something like that, right? After the same number of steps, it might be somewhere else. So you look at a large number of mosquitoes, and then what I had plotted here is there after a large number of time, I just plot the end point, the final position of the mosquito, right? So if you do this, so you can do this like if you, I mean, if you just write a simple, what is it called, simulation, uh, you follow one mosquito, you'll find that it ends up here. Another mosquito ends up here. Another mosquito ends up. I mean, it has not traveled much. It's almost at the center. Okay, so large number of mosquitoes will be distributed all over. So each mosquito you can't predict anything. But for a large number of mosquitoes, you can say exactly how many mosquitoes are there in between R2, R plus DR. Does that make sense? Any other? Yeah. Yeah. This one? Ah. Okay, so, okay. Yeah, so maybe now at this point we will show the experiment, okay. So, see, this is, I mean, we are doing one experiment, right? So what I said is that when you drop okay, so I mean, when we drop things from the top, like if supposing I drop 4 particles, okay, so there's a possibility that all of them will end up in the last box, right? It's a very small probability. Like if I hit 100 balls, is there a probability that all the 100 balls will end up at the last thing? So in one experiment, it's possible that I'll find that, okay, I drop things out from here, they do something. So typically, I expect this, okay. But there is also always a probability that it will, I might get some curve like this. It's a very small probability, right? So I will never get a perfect Gaussian. So this is the perfect Gaussian becomes more and more true when I take extremely large number of balls and I make a very big huge plot, okay. But when I have a finite number of balls, you'll always see some deviations from the perfect Gaussian, okay. So you will, I mean that this whatever I predicted from theory, right? I mean, of course, this is the number of balls that you expect. If you drop 2 to the power n balls, you expect so many balls in each box. Okay, so let me just give you a simpler example. Supposing I just have, I just have two pins, 3 pins. Okay, I drop one ball. I drop 2 balls. Okay, so where will they go? So there are many possibilities, right? So I can either, both balls can be here, that's one possibility, or one ball here, one ball, there are 2 such ways this can happen, or both balls can end at the, this third year, right? Now, I mean, if I do the experiment once, I could get this, or I could get this, or I could get this, right? So I won't always get, exactly this. Okay, so now, but if I have a large number of balls, what I'll find is that just one possibility becomes more and more dominant. Okay, so but there will be always be, it won't be exact, like what you predict from the theory. Okay, so yeah, any other questions? I mean, yeah. Yeah. Right, yeah. So what you're asking is, yeah, that's the amazing thing. See, so I mean, what you're asking is like, it's possible that the step length is not fixed, right? So first step might be like this, second step might be like this, third step might be like this, and maybe fourth step, and then like that, right? Okay, so now the amazing thing is, after a large number of steps, it doesn't matter. Whatever it is, you'll always get that same distribution. Okay, so this comes from something called central limit theorem. So this I won't have time to talk about, but it's so what it says is that if you sum a large number of random numbers which are chosen from any distribution, okay, so the distribution can be can mean that like you have paths of various lengths, okay. So whatever it is, when you add many of these things, the final thing you get is always Gaussian distribution. So it's a mathematical theorem, yeah.
Sir, is the Like the number of times the walk, like the steps take place, is that like defined, or is that random as well?
No, here I'm always looking after a fixed time. After a fixed time, where are the mosquitoes or where is the random walk?
Okay, so if it is only time, then could the mosquito have like a slow speed or a very have a higher speed or anything like
Yeah,
that?
see, those you can like make more and more complicated models. Like mosquitoes travel with different speeds and so on. Many things will, like even if you allow all these things, lots of things will remain unchanged, you'll still get. But then some things might change. But yeah, we won't go into that. What is the? No, it's just a Gaussian, so it's a Gaussian curve, right? E to the minus x square. So whatever value at the peak is that is the most probable. So most probable numbers is it's just yeah. There was question.
In the case of mosquitoes, of the random walk of the mosquitoes, we are observing a circular symmetry. So, can you explain a bit into the circular symmetry that we are observing? That why is it there?
Right. Yeah. See, I mean, so everything is after a large number of steps, right? So what I mean, just imagine if you have lots of mosquitoes starting from the center, like from this region, I release a lot of mosquitoes. After a long time, what do you expect? Do you expect any direction to be special? I mean, each mosquito is going randomly, right? Why should any direction be special? All directions are equivalent, right? It's every time it's doing that, every mosquito is doing a random walk. So there's no special direction, right? So, I mean, this is what you'll observe if you do a if you do an experiment or a simulation. Just after a long time, just look at where the mosquitoes are. Okay, so of course it's not a perfect sphere. That of course is true. But if you take more and more mosquitoes and look at large times, it will become almost like, of course, there's some deviations you'll observe, but more or less it will be a nice spherical symmetric distribution. See, those are maybe some details which we can discuss later because it's similar to what she asked. Like if the velocities are different, it will change a bit, but maybe we should stick to the simplest model first, right? It won't change things much. Yeah.
That so do such like natural phenomenon like about insects where they create groups and then they are attracted to something kind of resemble this question, or
Okay. So
was there
see,
any correlation like about this, even though we're taking the
no,
example of
no, see,
mosquitoes?
here there's really no attraction. If it was attraction, there would be a special direction. Like if there's food here, they would go towards this, right? The fact there's no, it's completely symmetric means there's no, it's completely random move. That's why it's random walk. Otherwise, it would be a biased walk. If there's food, then you'd see that this swarm should move like in some direction. Right? That would be a, yeah.
Probability that they are given, it's the probability to find them in the circular strip, right?
Right, yeah.
So we would expect it to have pi, but why is the solution independent of pi?
Pi. Why do you expect it to have pi? Okay, I mean, see, if like if it was if you ask what is the probability it is at xy, then okay, pi. This is okay. See, this is if you just integrate 0 to infinity, it's normalized to 1, to n, and to 1 actually. Right, so it's always normalized to 1. I mean, if you had done, okay, so in 1D, if you do, like I said, it's a Gaussian which looks like okay, so there's a pi. Okay, now if you do in 2D, it's actually what you can show is that what is the probability of finding it at position xy, then it's a product of two Gaussians like this. Okay, then you get a pi. Okay, and then you multiply by 2 pi r, I said, right, because it's between r2 r plus dr. So there's a factor of 2 pi, so that's why this pi gets cancelled. Okay, and this is what you get. Okay, I think maybe I should move and then we will take more questions. Okay, so now I'll talk about one other very famous example of random walks, which is Brownian motion. So this is one experiment. Okay, so what I'll show you this video. So how this video is, I think this was taken at ICTS, and maybe Iqbal might be able to show it to you in the lab. Okay, so you can ask him if you have some free time. I mean, this is one of the most beautiful experiments, I think, that simple experiments in physics. Okay. So what we do is you take a glass slide, put a drop of water, okay, and then take a, let's say, syringe, dip it in milk, and then just dip it in the water. Okay, so there should be very few like particles of milk that go into that drop of water. Okay, and then cover it nicely, and it should be sealed properly. Okay, so the system you are preparing is basically you take a kind of a slide, put a drop of water, and then introduce a few particles of milk on this drop of water. Okay, so these milk particles are typically about micron size. Okay, so that's 10 to the power minus 6 meters, right? So very tiny particles, and then you put them in a drop of water, and then you cover the thing. So if you have a microscope at home, you can also do it very easily. You have to cover it properly and then make sure that this is kind of sealed. Okay, maybe you can put Vaseline or something to seal it completely. Okay, so the reason you want to seal it completely is that you don't want any air motion and things like that. Okay, so it's completely isolated, tightly sealed. Okay, now you look at this drop under a microscope. Okay, so if you have a 100x or even 40x microscope, that's good enough. And what you'll observe is that, okay, so here what you see are the milk particles, which are like micron size, and there are all sorts of sizes of particles. Okay, so what you'll see is that they kind of keep jiggling around. Okay, so they don't. Yeah, so I mean, first time you see it, it's quite amazing. Okay, so you should imagine, like, for example, if I take a beaker of water, right, and I put some very tiny ball in it. Okay, what happens? It will just, okay, it might either sink or it might float, depending on the weight, right? If it's exactly balanced, kind of, then it might just stay wherever I put it, right? If it has the same density as water, then it will just stay here. But it's not jiggling around, right? It just stays where I put. Now, but why are these guys jiggling around? Okay, so this is quite amazing. Okay, so this is one video, and then I'll show you this other video. These are the same thing, but it's smaller particles. Okay, so it's clear that if you take the smaller particles, you take the more they jiggle. Okay, big particles, it's clear if you take a big particle that you can see, it doesn't jiggle, right? It just stays where you put it. Okay, but as you go smaller and smaller particles, somehow they start moving randomly. Okay, so this was first discovered by this botanist called Robert Brown. Time 4:30. Okay. I mean, made many like lots of discoveries, and he was obsessed with the microscope, and he looked at everything he could look at. He put it under the microscope and just looked at it for hours and hours, and he discovered this phenomena. Okay, so he put some stuff like this, I mean, and put it on the, so he didn't know what it was, like why are they moving. So first thing you will think is what would you think if you saw such a thing? You might think it's living, right? So he tried, I mean, maybe he just heat them up to as very high temperatures. Then he tried to take like rocks, I mean, samples from the pyramids and so on, which must be dead and so on. And he tried using it. So everything he observed, he saw this amazing motion. Okay. So he was, I mean, he didn't know what, at that time he didn't really know, but he knew that there was something very fundamental. Okay, so this was long, like this, look at this year, it was 1858. And the first theoretical understanding of this was first actually given by Einstein. So in 1905, he wrote, I mean, lots of amazing papers, which included Brownian motion, some paper on special relativity, and this famous paper where he showed the equivalence of mass and energy. So we'll talk about Brownian motion. So what did he really explain? Okay, so I'll tell you about this Einstein's theory of Brownian motion. So basically this is what a Brownian, if you look at those videos and if you just follow one particle for a long time, let's say after every 30 seconds, you plot its position, okay? So it does exactly what the mosquito was doing in some sense. It starts from the origin, after 30 seconds it goes somewhere, after 30 seconds it goes somewhere, after 30 seconds it goes somewhere. So in this case you can see the path lengths are also different, the angles are different, path lengths are different. And after, let's say, a few minutes, it might land up where? Here. Okay. So after a long time, it hasn't moved. Overall displacement is not much. It's here. Okay. So if you look at lots of such trajectories, natural, I mean, so, right, yeah. So this motion is like that of a drunkard. And in this case, I show after 24 steps, it's still not very far, right, from where it started. Okay, so now, so one of the things that you can measure is that on an average, you can ask after time t, how much distance have I traveled? Okay, so in this case, the distance traveled is very small, but there's another realization you might get where it moves like uh, the final point might be quite large, right? Some motion might be quite small. So, so R might be different in different realizations, okay? If you take an average over all realizations of this number R square, then what Einstein argued is that it should grow with time as t, and where d is diffusion constant, okay? So this is how like random walk evolves in space. It grows very slowly. Okay, with time it goes as root t. Okay, and what he said is that this diffusion constant. Now, what does it depend on? He gave this very famous formula. He said that this diffusion constant depends on the temperature of the water, the viscosity of water, the size of the Brownian particle, and that's it. Okay, and this Kb, which is Boltzmann's constant. Okay, so yeah, so maybe I'll just tell you very quickly where this formula comes from. It's not, you can see that, I mean, Einstein was using extremely simple arguments to obtain a really fundamental result. Okay, so his arguments is so this first part, all of you know. If I, like I just told you about this example of a small sphere in water, what you know is that if I drop a small particle with some mass, it will go down and attain some terminal velocity, right? And how do I find the terminal velocity? Huh? But what will be the final terminal velocity? Like if I drop a ball like or in water, it will reach some terminal velocity, right? How do I find it? When the what force? Buoyant force. Okay, so that yeah, so buoyant force equals to gravitation. That is that doesn't give terminal velocity, right? That just says whether it will go down or go up. Viscous force, right? Yeah, buoyant force and viscous force, right? Exactly. Sorry, maybe that's what someone was saying. Okay, so there are the basic forces acting on it are, one is gravity, which is just mg, and then there's a buoyant force, which is how much? No, buoyant force. It's the weight of the volume of the water displaced, right? So it's 4/3 pi a cube, that's the volume of water, into the mass of water, right? So density of g, right? Okay. So this is the buoyant force which is upwards, and what is the viscous force? If it's moving with velocity v, 6 pi eta av, right? Okay, so now if we have to basically balance this and this, so the final terminal velocity is given by mg minus, okay, so let me just call it some m effective into g, that's the downwards force, and this is equal to 6 pi eta a v, this gives me the terminal velocity, right? So I can, so what I'll find is that this ball after some time it's moving down with some velocity, okay. So if I have a large number of balls, then I'll basically see that everything is falling down at some terminal velocity, okay. And then there's some current flux of particles, okay. But now what we know is that if there's a large number of particles which have settled down, then we know there's something called diffusion, right? Everyone has heard of diffusion? Yeah, okay. So diffusion means if there's like a lot of particles here, they should start moving up, right? Right. So and then okay. So first there's a terminal velocity which is given by this, and this causes a downward flux of particles which is given by this, right? Rho times that this is the density of density of not water, but density of number of particles per unit volume, okay, of the Brownian particles. Okay, so density times velocity gives the flux, right? So this is the flux of particles going down, and then when they settle down, there's a upward flux due to diffusion, which is given by this formula. Okay, so if you have not seen this formula, doesn't matter. This is, it basically says if from higher density to lower density, there's a flux, okay, and the gradient of the density gives the current. Okay, so now what Einstein said is that, I mean, eventually, okay, so if we put marbles, of course, we'll see everything goes down, right? But if we put something like ink, which also has tiny particles, then eventually what you'll see is that it's not like all the ink goes and settles down. You'll find a gradient of ink, right? There's a steady state where there's high density here, and then the density slowly decreases as you go up. Okay, so a steady state is reached where things, I mean, this downward flux is balanced by upward diffusion. Okay, so there are two processes which balance each other, and if you just, so this is what I've written, this downward diffusive current going up is balanced by the flux of particles going down. And if you solve these equations, if you, okay, so the other thing is that there is, in the steady state, what we know is that the density of particles should go down with height in some exponential way. So this is related to the law of atmospheres that you might have read. And so using all this, what you can quickly derive this relation between the diffusion constant and all these other constants. Okay, so okay, so what have we, so any questions? And I'll stop here for 1 minute. Yeah. Which electron cloud? No, there's no, I don't think. Which electron cloud?
No,
Like, so
like
if
ground.
electrons are, of course, doing a random walk, they would do
No, like
it.
ground state of an atom. If we see, I mean, an electron. If we see,
No,
It'll,
that is very different. That follows from Schrodinger's equation, right? It's not a random motion. Though it has the same form, I think, yeah. Okay, so I hope so here what I basically I'm trying to show is that I mean so what can you learn from the Brownian motion, this random motion that you see? First, you can observe, what you observe is that the distance of a particle increases with time in this way, and there is a constant that you can measure in an experiment. Okay. And then Einstein said that this diffusion constant is related to all other constants that are related to the fluid, like its temperature, viscosity, and so on, using this formula. Okay, and then I just gave you a derivation of this formula. Okay, so okay, so now I'll just show you one. I mean, like why this formula is so important. Okay, so now if this formula okay, so this is the basic formula. Now what I've written is this Boltzmann's constant is related to the gas constant divided by Avogadro's number, right? So then you can rewrite this formula and write Avogadro's number is equal to this, okay? So now this formula is really very nice because this formula was actually used to kind of, it was the first experiment which allowed us to determine Avogadro's number in a very direct way. Okay. So this is an experiment done by this person, Pera, in around 1909. So what he did was exactly like the video I showed you. So he looked at under his microscope and he tracked Brownian particles. So at that time there was no video and all, right? So what he took, he just took a graph paper and he just followed after every 30 seconds he would plot the position of the Brownian particle. Okay. So it's extremely hard work. Okay, so he tracked like hundreds of particles. I mean, you can imagine how much patience he has. And so after, then you take an average over all these R squares. So for each experiment you get a R square, you take an average over 100 experiments and you find the diffusion constant. Okay. So from the diffusion constant, then once you know the diffusion constant, you know these other things like viscosity of water, you know the size of the particles, you know the temperature and so on. And then using this formula, you can find the Avogadro's number. Okay, so this is the number he got at that time. So this was one of the first accurate demonstration of Avogadro's number. And for this, he got the Nobel Prize in 1926. Okay. Okay, so see, this is, I mean, just looking at some completely random event, you can actually extract so much information, right? So that's, that's a sort of amazing thing. Okay, so, I mean, here I just want to give you a sort of more microscopic view of this Brownian motion. See, Brownian motion, I mean, if you could see what a Brownian particle does under a microscope, I mean, we can't see all the water molecules, right? But basically something like this happens. This is the Brownian particle, which I said is like micron size, and all the other water molecules, they are like 1,000 times smaller, okay? They are like nanometers, okay? So here it's much bigger, the difference is not so much. But I mean, this is what happens. There's a huge molecule in a sea of tiny, tiny, tiny molecules, okay? And then somehow the motion of this single guy is kind of simpler, okay? So in fact, you can just now we discussed like what is the equation of motion of this particle, of the colloidal particle. So we wrote gravity and buoyant force and then viscous force, right? But there's an additional force, right, which is coming from the fact that particles are being hit randomly by this particle, by the smaller particles, okay? So this is called a noise term. And this equation then completely describes this Brownian particle, okay? So even though it's a very complicated system, like billions of particles, small particles hitting these small particles, but somehow finally you can write a very simple equation just to describe this motion of the Brownian particle. Okay. So this is called the Langevin equation, and this is one equation which we use a lot in our research. Okay, so basic idea is, why are we able to write such a simple equation for such a complicated system? And the basic idea is randomness and the law of large numbers. I mean, this big particle is being bombarded by large number of random forces. And when you add up lots of random numbers, you somehow get predictive, you can start predicting things. Okay, so this is another viewpoint. I mean, like, each Brownian particle moves randomly, but if we observe a large number of them, then we can make predictions. Okay, so here what I show is an experiment where you take a drop of ink in a two-dimensional plate, and you just observe. So what is ink? Ink is again large number of random Brownian particles. Okay, so each guy is doing a random thing, but if you look at the whole thing, then it spreads in a nice way, right? It has a very deterministic motion. And the size of this ink blob actually again follows the same law, and this diffusion constant is the same diffusion constant that we got there. And what you can show is that the density of this ink molecules follows this nice diffusion equation. Okay, so someone asked, like, how do I solve that? How do I get that formula that Rayleigh had written, R into 2 minus R square? So if you solve this equation, you'll immediately get this is very easy to solve this equation in any dimensions, and you'll immediately get what Rayleigh observed. Okay, so the Rayleigh's formula follows from this equation. Any questions? Okay, so this is again another experiment which I will ask people to just try and do it. See, experiments are very, tricky. Like, even though it looks like it's very simple, but you should just do it on your own. Typically it won't work. Okay, you'll find that it doesn't follow anything like what you. So you have to try a lot to make it work. Okay, so it's, it's always good to do experiments, because this is a very simple experiment. You just need a stop clock and put ink and just watch it, right? But you'll find that there are a lot of challenges, and it's good to do this kind of simple experiments. Okay, I still have 10, 15 minutes, right? 10, that's okay. Okay, so I'll give some other examples of like where you see randomness. And this is in, like, if you look at a bacteria, that's micron size, right? So that is a particle which is affected by this random noise that I talked about, right? So I said that this random forces start acting whenever this like size of objects become very small, right? So bacteria is some object where this random forces become important. So if you observe a bacteria, you'll find that they move in this sort of random way. Okay. And that's because, because they're in an environment where they're being kicked around all the time. Okay. Now it turns out that bacteria is different from a milk particle, because it has some energy on its own, right? It tries to do things, so there's an internal drive. It's not a dead object. So people write different equations of motion for to understand bacteria. So this is again sort of a very interesting and open area of research called active matter physics, where basically you try to understand, like, this kind of objects which are in an environment where noise is important. Okay, so you can write simple equations to understand this this kind of things, and these are called active Brownian particles and so on. Okay, so yeah, so I won't try to explain these equations. And then you see all sorts of interesting things when you take large number of these particles, and there's something called collective phenomena. Okay, so even though each particle does something quite random, when you put lots of them together, you find that you get what is known as you can get a lot of nice patterns and so on. Okay, so this is some experiment from, I think, 4 or 5 years back, where you take a petri dish and you put lots of bacteria. Okay, so this is the experiment. Okay, so in the experiment you put lots of bacteria. Initially they are put in just randomly. Okay, and each bacteria is trying to move in some random way. But after some time, what you find is that see, initially they are all random, but after some time, so this is a simulation of the same thing. Okay, so in the experiment it's difficult to see, But in the simulation, you see that after some time they form, I mean, every guy is moving like in a nice pattern. Okay. So this pattern emerges just from this whatever random forces and things that are acting. And okay, so this you can do experiments and simulations and understand these things in great detail. Okay, so finally I'll just talk a bit more about the kind of research that I and in my group we do. So basically, like I said, like we do statistical physics, and the idea is to understand macroscopic phenomena from microscopic. So microscopics means you all know Newton's equations. You write equations of motion for all particles, and macroscopic phenomena means basically things like thermodynamics, where you don't care about the particles, but you measure things like pressure, temperature, volume, and so on, right? And how they are related and so on. And you can go from microscopics to macroscopics using statistical physics. Okay, so I mean, so the basic idea is again, like if you have like huge number of 10 to the power 23 particles, number of particles moving in a box, you can't, it's difficult to say, make any predictions. I mean, from Newton's, by solving Newton's equations, right? It's impossible to solve. But because there are large, once you have large numbers, you can still make accurate predictions, okay? So, I mean, like if you take a gas, I mean, what you see is that as you increase the density, I mean, then at some point it forms a liquid, and then as you increase the density more, it at some point you'll form a solid. Okay, so I think you should see. Okay, so here we don't want to follow each molecule, right? That's too complicated. So even though, and yeah, so as you increase density, you get a solid. Okay. So now, I mean, it seems like this is a very difficult system when you think of Newton's equations. But in statistical physics, which was founded by Boltzmann, there is a very simple prescription. Okay, so there's, I mean, or given, let's say you are in this room, and this is a gas filling this room, and you have like a huge number of molecules moving randomly, right? But all you need is the total number of molecules, the volume, and the energy of the molecules. And given this information, you can write some function called an entropy function, which actually contains all information about like what is the pressure in the room, what is the, how are pressure, temperature, volume related, and so on. So you can derive this from this function, everything about thermodynamics. Okay. So this is how like you can use like statistical physics to make predictions about very complicated random systems. Okay, so here, I mean, I give, there's something called non-equilibrium statistical physics, where one is interested in things like water flowing in a pipe, where if again, if you look at the microscopic level, it looks very difficult. But if you kind of look at a coarse grained picture, then you can, I mean, coarse grained means you don't care about the individual molecules, you just care about how many molecules are there in some, the density of molecules and maybe pressure and so on, right? Temperature. So like when I put a thermometer, I don't care about what the molecules are doing. It just records some average thing, right? So, I mean, so in this room, even, I mean, finally what matters is like what is the density of air in different parts, what is the temperature in different parts, and what is the pressure in different parts. And then I can write equations to describe how these different quantities evolve in time. Okay. So this is something called hydrodynamics, and there are equations which tell how this evolve. So I can forget about all this huge number of degrees of microscopic degrees of freedom, and finally write very simple equations. Okay. And make a lot of predictions. Okay, so I'll end with this one last example. Okay, so these equations that I just wrote, okay, so they can make really, I mean, make predictions for things which look extremely difficult. Okay, so for example, I mean, everyone has seen this movie Oppenheimer recently, where you see this huge atom bomb explosion, right? So it's a, I mean, it's a very like it's a extremely So what is the event? It's a huge amount of energy being released in a very small place. Okay, so it's a very extreme violent event. Okay, and now what can you say anything at all about this system? Okay, so it turns out that from these equations that I just wrote, you can actually predict a lot of things. Okay, so all you need to know about this explosion is like what is the energy that was released in this explosion and what is the density of air. Okay, so if you know that, then you can, okay, so this is a picture of the explosion after at different times. Okay, so you can see there's a shock which is exploding. Okay, and so this is in milliseconds, so it explodes extremely fast. Okay, so you can plot the position of the size of this blast as a function of time, and you get some curve. Okay, so this curve, the radius grows as t to the power 2/5. Okay, so now this, I mean, this looks. I mean, how do we understand it? Okay, so it turns out that this formula was actually written by so there are three famous physicists. Uh, Taylor, von Neumann, and Sedov, a Russian physicist. Okay, so they wrote this formula just using these equations. Okay, and see I mean, you can imagine how much powerful this equation is. Okay, so it uses very little information. You just need the energy of in this blast, and you need the density of air. Okay, and this A is some constant which one knows exactly, and it tells how this R goes with time. Okay, so these equations were written, I mean, before the blast, and then if you fit the data, it fits like perfectly. Okay, so this is the power of statistical physics. And in fact, this Sedov was a Russian. He was sitting in Russia, and using this equation, he could actually predict how much energy was released in the blast. Okay, so this is quite amazing. Like, I mean, yeah. So this is what I want to. I think this is my last slide. So there's a lot of information in what appears to be random numbers, and the main idea is that there's this thing called law of large numbers. Whenever you have large numbers, they lead to simplicity, okay, and you can make predictive laws. Okay, so I think I'll end with this. We'll just do this demonstration of the Galton board, which that's where we started. So let's see if this works. Okay, where do you? Okay, so this is what I showed right in the beginning. Maybe I'll just go to that slide. It doesn't matter. Okay, so yeah, so here there's a triangular lattice out here. So this is made using a 3D printer. Okay, so Iqbal made it like a couple of days back. So it's still not perfect, as you will see. And but you can make it also using like if you just do a Google search, you can easily find material like just simpler material with which you can try making it. Okay, so that's thing you all can try. And so here we tried lots of different material which we'll pour into out here to get this Gaussian. So we tried things like suji and mustard seeds and steel balls and then the sand. Some things work and some things don't work. Okay, so that's also something to understand. But I'll show you two of them: the mustard seeds and the suji. Okay, so just. Okay, so is this visible? Yeah. Okay, I think I poured too much. Okay. It's not visible, is it? I can't see. Oh, it's there. Okay. Okay. So now we shouldn't pour more. Okay, because it's because the peak is reached. Okay, right. We shouldn't pour more because if we pour more now, it will just spread. It's no longer the. It's not coming from what we the physics that we want to understand, right? Because it's reached the height. So we should stop here. I already poured too much. Okay. Otherwise, you'd see that the central peak should be more, and then the side peaks should be less, and so on. So now, of course, this is not a perfect, like if you try to fit it to a Gaussian, which I haven't done, but it has some shape which roughly looks like a Gaussian, right? Someone asked like, there were some small deviations, okay? So if I do it large number of times, each time it will be a bit different, right? But on an average, it will be like a Gaussian. And if you make a bigger thing and like if you make a big Galton board, it will be more, it will look more closer to a Gaussian. Okay, so it's, see, the large number is important. So it becomes really Gaussian when it will become a perfect Gaussian in the limit n going to infinity, right? So right now it's not so perfect. Okay, so now let's just try mustard seeds. It's okay. Okay, it's not. Oh, sorry, it's reached the maximum height. We shouldn't do it above the height. Okay, so it didn't. It's okay. It's worse than the previous one, right? Okay. Okay. So and with steel balls, it's even worse. Okay. But now, I mean, so this is the point. I mean, like experiments are much more difficult than theory. But then you have to go back and ask, why is it not working? Okay. Like from the theory, there's a prediction. Why is it not working? Okay. So in this, I mean, this we just made a couple of days back, and I can see a number of reasons why it won't work. One reason is the width should be a bit bigger. Okay. The reason is that it's going some number of steps, but after that it reaches the boundary. Okay. So if the width, if it's a very narrow channel, obviously it can't give you a Gaussian, right? Just imagine the extreme limit. If it's very narrow, you'll have like a flat A. So it should be much more wider than its A. Okay. So, and the other thing is when you drop, see what is the model that we used. The model that the theoretical model that we are that we are using says that when it drops, it does this and this and so on, right? Now, if you have like steel balls, what I saw is that when it drops, it might go like that. Okay, it's very heavy, right? So it might actually, it's not a perfect random walk. And it's a small box, so it will quickly become uniform. Okay, so with steel balls, it actually becomes kind of more uniform. Okay, so you'll see a Gaussian if you do it correctly. So it's a challenge to do it correctly. So I hope some of you will try to figure out how to make it work. Okay, so experiments are always hard. Okay, I mean, so that's why people don't like doing experiments because they're kind of difficult. But it's really, I mean, I think, I mean, of course, finally, quite often you want to understand, like, this is the phenomenon, how do you understand it? Okay, so whatever you see, can we write a model to explain this? Okay, so maybe it's not like the model we wrote, it's not good. So how do we explain whatever we observe? Okay, so in this case, for example, if you take the fact that it's a narrow channel, you can, so what happens when it goes down? It at some point it will hit the wall and then it goes back, right? So you have to take that into account in the model, and you can explain whatever you see. Okay. So when your experiment doesn't work, I mean, I think this is really important. Like in BSc, when you do experiments, and most of the time it doesn't work, but I think you should try to really sit and understand why it's not working, and make sure you understand that. So I'll stop with that.
For this one, the opening is right in the middle. So if we put it on the side or something where you have a boundary, would we expect like half of the curve
Yeah,
or something like that?
I mean, yeah, so if you put it at the edge, I mean, you have your triangular lattice and you drop things from here, right? That's what you're saying. Yeah, then of course it will be completely different, but you can, if you write your model, you can solve it and predict exactly what you will get. Yeah.
The experiment with bacteria in a centrifuge, right, in a rotating,
Right,
have they done it with dead bacteria?
No, it was
see-
not rotating.
Oh,
So it was you just take a bacteria in like this food in it, and the bacteria are active.
I see.
And you just put, and then they automatically just start this,
They automatically do that. Okay,
do that, right? And actually, the fluid in the center is moving in the opposite direction. I mean, I didn't, but it's a strange pattern. At the edge, it's moving in one direction. At the center, the fluid is moving in the other direction. So
Okay,
somehow, spontaneously, it goes into that pattern. Yeah. I use the microphone. I think there's a microphone there.
Biology, we learned that sampling something, when we sample and then we plot a graph, we always get a Gaussian distribution. Like for example, you visit an area and then try to take an account of the age of the trees in a region, and we plot a graph, we get a Gaussian distribution. Why is that so, sir?
Right, yeah. So this is what I told you about this central limit theorem, right? I mean, it says that if you, let's say, okay, so the assumption is like if you go to a forest, I mean, the trees have random edges, let's say, right? So you take, so let's say xi is the age of the ith tree, right? You take a large number of trees and you look at their age. So then you're saying that what you find is that the distribution of xi is a Gaussian. Is that the statement? No. What is the statement? If you plot the age distribution of the graph, okay, so let's say, okay, this I don't know why it should be Gaussian. Yeah, this I don't, I mean, if you just take the age of trees in a forest, I don't think it should be a Gaussian. I don't see why. Sorry? Yeah, so if you, no, mean of the ages means, okay, so if you take many trees and find their mean age, okay, so let's say sum over xi and 1 over number of trees, I equals to 1 to, let's say, n number of trees. If you take and find some x bar, right? So then if you plot the distribution of this, that will be a Gaussian. Okay, so this is like, I mean, so each tree has an edge, let's say, which is chosen from some distribution. Okay, so this each tree has an edge which is chosen from some, let's say, some, it can be any arbitrary distribution. Okay, so I mean, so this is edge, and this is the probability that tree has this edge. Okay, so okay, so I mean, okay, so let's say you go to a forest where trees have edges according to some distribution, and then you randomly choose n trees and form this number. Okay, then if you plot the distribution, okay, so what does it mean to plot the distribution? You take n trees, you get one number, right? You take another n trees, you get another number. You take another n trees, you get a number. Okay, so now you take all these numbers and plot a histogram, then you'll get a Gaussian distribution. Okay, and that's the central limit theorem. Whatever, like this excise might have some very strange distribution, but when you add lots of these random numbers, the distribution that you get becomes a Gaussian. Okay, so that is, I mean, that's so yeah, that's basically the idea of the law of large numbers. There was one question here. Yeah.
So basically what we are seeing here, that order is emerging out of randomness. So can it stem out from the fact that entropy of a system keeps, the entropy keeps on decreasing and it doesn't increase? Is it related to the fact of the entropy of somewhere to entropy of a system?
No.
Or the
See, entropy is always increasing. See,
yeah,
like when
entropy
I
of-
put, let's say, so by order, of course, what I meant is that, okay, it's not really, I shouldn't always, maybe it's, what I really meant was that you can make, you see some patterns, and like, for example, if you look at the mosquitoes, right? See, eventually they are all spreading, so entropy is increasing. Or if you put ink, right? When ink is in some small region, it's a low entropy state. When it, if you let it evolve, it diffuses and it spreads, it becomes homogeneous. That's a high entropy state. Okay, so entropy is always increasing. But the point is that you can, even though things are happening randomly, you can make a prediction of how it's spreading, how exactly it's spreading. So in that sense, like there is some order in the probability distribution. Okay, but it's not order in the sense of entropy. I mean, entropy
Okay,
is always increasing.
so in that sense, that randomness is different from what we talk about in the randomness of the entropy.
Right, yeah.
I just wanted to make a comment about this. There is a notion like entropy-driven ordering, like in the sense that if you take the free energy, it has an energy and an entropy. So E minus Ts, say.
Right, yeah.
So you can either have a situation where you're minimizing energy or you're maximizing entropy. And so, for instance, there are these examples in soft matter. If you have colloidal particles of two sizes, then, and these are hard spheres, and this completely entropy is the only factor in the problem. But on the other hand, it undergoes a phase separated situation, which is completely ordered. So you get order out of disorder, so to speak, because it's entropy driven order. It's not energy driven order.
Right, yeah. I mean, yeah, so, yeah, I guess one other example might be, yeah, if I, for example, if I pack hard spheres in a box, right? So this I showed a video at when the density becomes large, then what you see is that it becomes a crystal, like a crystal, right? So now question is, I mean, why is it a crystal? Okay, so what you can show is that the when it's a crystal, the, I mean, so in this, okay, so like what Supurna was saying, in a hard sphere system, so normally you have free energy is energy minus Ts. Okay, so maybe you have seen this relation. But in a system like a collection of hard spheres, there's no energy in some sense. There's only entropy. Okay, so now, I mean, why does a crystal form? Okay, so you might think that a crystal forms because it's the lowest energy state. Okay, right? I mean, so a crystal is like a perfectly ordered state. Okay, so it might form because it's the lowest energy state out of all possible configurations of the molecules. Okay, so now in a hard sphere, all energy, like if, because there's no, hard spheres means like this steel balls, they don't attract or do anything. They only when they come in contact, they interact with each other. Okay, so there's no energy of all configurations is exactly the same. Okay, but still they form a crystal when you go to high densities. Okay, and that you can understand by the fact that if you actually compute the entropy of such a ordered state, like entropy means how many configurations are there which are like have this order, then that is much larger than if it's in a completely disordered yeah. Okay, so in that sense you can. No, see in this case there's no medium also. It's just the hard spheres are the objects. Okay, but like a state like the crystalline state has more entropy than a disordered state. So that's why you get a crystal even though there's no interaction energy. Right, yeah. Right, yeah. Okay, so yeah.
Hello. You just said that a crystalline state has more entropy than a disordered state, but then doesn't entropy increase with disorder? So the crystalline state should essentially have lesser entropy.
Yeah, so this is counterintuitive. I mean, like you might think that a disordered state should have more entropy, but for a crystal, I mean, you can show that the, okay, so what does it mean to say more entropy? Okay, so if you take a, let's say, okay, let me draw a crystal more clearly. So let's say like, I mean, a triangular lattice, right? A two-dimensional crystal formed by a triangular lattice. Okay, so now this is a crystalline ordered arrangement of A. Now the same spheres, I mean, so I mean the same system. Okay, so it's bounded. So there's some fixed density of like number of spheres per unit area. Now this, instead of this arrangement, it's possible that I can arrange these same guys in the same number of spheres in a random configuration. Okay, now what does it mean to say this has more entropy than this? Okay, so what I mean is entropy basically of this state is like keeping more or less the same configuration. I can move these spheres around in lots of ways, right? Okay, I'll just come to you. So I'm saying like you have to count how many different arrangements are there so that I can, for example, I can move this ball here, but it still stays more or less in this pattern. Okay, so I can move these things around and count how much, like how many configurations are there. Okay, so that gives me the entropy. And now for this random configuration, I can do the same. Okay, I can move them around randomly and ask how many configurations there. It turns out surprisingly that this has more entropy. Okay, that's why when you increase the density sufficiently, the system naturally chooses to be in this state rather than this state. Yeah. Yeah, rubber is a good example, right? Yeah, that's a very similar example. I mean, so if you take, I mean, so rubber, I mean, one way to model rubber is actually by a random walk. Okay, so you can say rubber is a polymer. Okay, so it has like, you can think of it as monomers, which are doing kind of moving randomly. Okay. Now, so usually, I mean, like if you just put it in, so this is of course it exists in some environment like a fluid or whatever. Now you can, if you just put a polymer in water, like, I mean, any configuration is equally likely, right? It can be completely straight, it can be completely folded. Okay, it costs the same energy, but typically you'll find that it kind of stays coiled. Okay, and you need some force to stretch it. Okay, now why does it prefer to stay coiled? So if you take a polymer like that, it's a random object, it prefers to be like this rather than like this, even though they're exactly same energy. Okay, now what the reason for this is that there are a large number of configurations which look like this. So this has much more entropy than this. Okay, so it prefers to be this in this state rather than this, and you need actually some force to pull it from this to this. So yeah, so here, I mean, the large entropy state is somehow the preferred state, right? I mean, that's, yeah. Okay. Yeah, any other questions? Anyway, so if you have more questions, you can always like, so I'm in ICTS, so you can find me and ask me anytime. Right, yeah. So if you stretch a rubber band, so when you stretch a rubber band, its entropy goes down, right? So if you do, huh? Goes down. So if you do that, and so if you take a rubber band and like put it on your forehead or on your lips, I think, and stretch it, you will find that it cools. This I always forget. Huh? It releases heat, so it you feel some heat, and when you release it, you'll find it kind of cools. Okay, this I mean, yeah, you can try it. I mean, huh? Yeah, there are a lot of rubber bands. So is it okay? Okay, right, yeah, right, yeah. Yeah, so actually random, I mean, polymer physics is another place where random walks are used a lot. And you can understand a lot about polymers just using this various models of random walks. Okay.